this data being in MNI space and displaying on the FS average surface. Okay. It's not relying on anything any free surface subject specific analysis, because I don't think those have been imported into this analysis pipeline yet, right? This is all MNI space, right? Sol?
Right. I guess I don't even mean to the surface, but with SPM, you can look at the activations on like pseudos surface.
Right. So yeah, that level of display, yes, you can do. And let me recall the syntax for that. I think it was called. I don't recall what it was.
What's the typical threshold on activation here?
So as far as I could tell, it ranged between like 2 and 3, but I don't know if this is.
I think by default it's trying to show you only like the top 5% or 10% or something like that. I don't recall what is the default, like the threshold value, but it's set to a percentile level basically of your.
I also noticed that when I was comparing just loading up the same images in Freeview, that these images looked a lot more. The ones in the QA report looked a lot more like the T maps than the effect size contrast maps. But I don't. Is that possible? That could be.
It might be. Let me remind myself how these are generated. I think they represent contrast, but I'm not totally sure. Let me just double check. That would be, what was it, 23. So yeah, those are contrast values. They come from SPM, XCon, VCon. So that should be just contrast values instead of... and you can actually check in there if you go to effects in the up left menu, where it says effect.
Oh yeah.
Info, it will tell you which file they're extracted from. Right. So it's com_0001, so that's contrast volume, right?
Okay.
That looks pretty good.
So yeah.
And this other thing that I asked about, having it, like showing it on the surface, is only useful if you're not comfortable localizing the activity.
Oh, sure.
On the slices. Yeah. It's not necessary. When I look at this, Alfonso, you can jump in and tell me what. So when I look at this, what I'm looking for is there activation, when you look at the speech-on baseline, which is a good baseline to look at. Is there activation in motor cortex? Is there activation in auditory cortex? How the sort of size and the size of the cluster and sort of the peak activity in those areas, how does that relate to activity elsewhere? So if that activation is relatively low, even if you have activity there but it's relatively low, and you have little tiny blotches all around, that could be a sign that something's not right. But with the other QA, we know that while the alignment's pretty good, it seems like things are going well. So even if that was the case, you might still want to include the subject.
Okay. All right.
Right, and also look at the negative side of the activation, which should follow something like a default mode network, because this is like an active task condition versus baseline, which was purely rest. So, and that looks reasonably to have like a medial prefrontal stuff and the lateral parietal stuff as well in there.
Okay. The next one, in
terms of where the activation is and the size of the activation and whether they look patchy and noisy or not. So this, for example, looks a little bit more noisy because all of those like frontal, lateral bands look like motion-related activation. So it might just happen that the subject has motion correlating with the task. I should probably, I haven't done that yet. I'll probably add a plot that shows you motion correlation, correlated task activation.
This person only had about 50% valid scans, like 70 valid scans, and then there was also a high amount of...
Also a very high amount of average motion and min and max motions, right? Valid scans What was the number of valid scans in that subject?
70.
70. Okay. So yeah.
Yeah.
Is that the minimum number of valid scans across all subjects?
Is that the lowest? Let's see. No.
Should you manually add these labels back? We recommend recording them, or they all like
Oh no! So this just this generates this plot based on the artifact detection portion of the processing.
Yeah,
We can take a step back.
I just feel bad. This is just such a
Yeah.
dumb question.
Well,
I found the
They're good
directory
questions.
labeled
Yeah.
This is one reason why the subject labels should be relatively small. Like instead in this example, we have like a SRI, MRI underscore. I don't remember. We have very long subject labels, which makes all plots and all of these things a little bit more.
Yeah.
Necessary.
So the one subject we were looking at, RI06.
Right. It's probably it's the lowest number. So
Yeah, it's among the lowest.
So can we do the same thing for subject 6? Can we look at the time series just to see the location of those scans, motion, and whether there is anything else that might be worrisome in there? Yeah, that plot exactly.
Again, I think I had specific comments.
Right. So
Yes, there's still motion in the corrected.
So it seems like the first two sessions were very noisy, and perhaps the third session was much better.
Yeah, it's that way.
Okay. I also changed the defaults. Remember that there was a point that we had the defaults to, that we had a discussion whether to change the defaults or not, to have a session-specific estimation or not. And
Yes.
I think I changed that already to be session invariant estimation.
Yes, and that's what this is.
And this is helping in this case, because otherwise the second session, it will be impossible to estimate anything out of there because most of the data points have been removed. So,
Right.
so that's fine.
I mean, is the amount of residual motion that's here, like, I don't know if you can see this at the same time resolution. It's like there's some like scans that are clearly.
Yeah. Yeah, that's fine. Pretty much the entire second session is out, except a few valid points that are just interspace there.
You can also see in the design matrix.
Right, and probably the second, the first and second sessions have a huge amount of number invalid scans. So those are those that diagonal looking. Yeah, pretty much everything is being removed from the second session, and the first is pretty much is okay.
And it also says that
that nothing in the second session is estimable. That's fine. But did you look at the contrast plots just to make sure that the contrasts are estimable?
You mean the contrast, like the contrast.
Right. So if you go to the plots and look at the one that is called SPM contrast, that is
I also
one of
noticed
them.
that there are two of these.
Yes, I'll probably remove one of them. There was a question of whether. Yeah, I don't know. I was generating two just to have, because there is an option to remove any contrast that is not using all truly estimable effects. And if you use that option, then you will have two different contrasts: the ones that you had before that removal and the ones that you had after that removal. And then that is unlikely to be used in general. So I'll just remove the generation of the two contrast plots and just keep one. So in your case, it's going to be the two plots are going to be exactly the same. So.
Oh, okay.
And yeah, that's all white, so that's just fine. Yeah. So if something is noisy, it will appear. You will get like red messages, telling you that something is wrong, and also some black portions either on the top, like below the title, or to the left before that label to the left. And if you don't see anything black in there, then it means that all of your contrasts are estimable.
Okay. So when most of those, all the scans from the second run are non-estimable, does that mean
right?
is it just not going to take those into account?
Yes, it's simply going to skip none of those are going to be used when estimating the actual contrast sizes for when looking at a Speechman's baseline. It's only going to be looking at the scans that actually can be estimated, and it's going to be disregarding anything that is in the second second session. So that's fine. That's all taken automatically into account, unless you want to change the option that says the model underscore session. When you have this scenario, if you change that to look at session specific things, you're going to get a lot of second section stuff that you cannot estimate actually. But in this case, since you are not estimating any session specific contrast, then you're fine, because those are simply going to be disregarded, the bad data points and the entire second session when estimating the Speechman's baseline contrast.
Can we just chat a bit about what's plotted here? I think this is my first time seeing this.
Yeah, at least keep up when they were running and then disappeared. I want to know about that as well.
Yeah.
Alfonso, can you just quickly
say what this is? Okay, so yes, in the rows of these metrics are let me see if I recall exactly. The rows are your actual effect sizes, the things that are in your design matrix. Basically, the columns are the regressors in your design matrix, and in the x-axis are the different contrasts that you estimate. So in this case, we are defining 4 contrasts, and each of them is defined only on 3 things that are the things that are being estimated from my first level design. The effects, the regressors that are being estimated by the model are the baseline, N-speech and R-speech thing. And the first contrast is the first column is just weighting those 3 effects with different numbers, and the colors represent the numbers that define the actual contrast definition for that particular contrast. So in the first contrast, we are looking at the average of the 2 conditions versus the first one. In the second contrast, we are looking at the difference between the 2 speech conditions. In the third contrast, we are looking at the difference between the first speech condition and the baseline, and this last contrast is looking at the difference between the second speech condition and the baseline. And those are just showing the actual contrast definitions. And then for every in the top, you see like a horizontal line that says contrast estimability. That thing, if that is all white, that is perfectly fine. If some of those 4 contrasts is not estimable or is not fully estimable, it's going to appear either as in gray or as in black. So, and the same thing for the individual, for the rows. In the left of this thing, you see a parameters estimability. Yeah, that thing. And if that is white, that is telling you that all of the 3 parameters that are being estimated by your first level design are actually estimable. And if some of them are not, they will appear in black. And also sometimes you will see messages written in red and bold letters telling you that something is wrong for some reason. And those are just try to detect particular things that might have gone wrong in the estimation, and that those could vary. I mean, you could have not enough degrees of freedom to estimate some of these things, or you could have like a lot of combination of non-estimable stuff. So those try to detect potential weird things that might happen. If you don't see anything in red and you see all of those bars in white, then you're perfectly fine. And you just look at the colors just to make sure that the contrast definitions make sense in what they were meant to be, so that you're actually defining the contrast correctly. So it's just a quick check just to make sure that those 2 things happen.
Okay. So now that we know those are okay, that they're estimable, if we look at the results, the speech minus baseline.
Right. That will just, the first contrast was the average of the 2 speech conditions minus the baseline. So that's the one that this is showing.
Right.
And this doesn't quite look right. I mean, at least to me. I mean, it has some indication of some temporal lobe activation, which is fine, and perhaps that, I don't know. But the negative, I mean, those big like ribbon-like looking sections of the activation and shows like a negative activation, which means it's probably motion related, I think. So that probably indicates that there are still, even after regressing out all of the motion covariations and all of the removal of all of the noise, all of the outliers, there is probably still some task-related residual motion. So
is motion just something we should assume whenever we see sort of like that halo, or is it?
I'm sorry, I didn't hear the question. Could you repeat it?
Is motion just something we should assume or just check into anytime we see that halo, or is it just in this case where it's like, well, this task shouldn't have it?
Right. When you see anything that is like activation at the border of the brain, and in these plots, well, and it's kind of like a ribbon thing looking activation that spreads over many different areas, but the thing that they have in common is that they form like a ribbon on one side of the brain. That is typically an indication of motion. That is just how it looks. You probably could look at the temporal profile and kind of like identify components like from an ICA, and you will see also that it has like high frequency component like temporal, so the changes in the signal are typically higher frequency than the activations that you typically care about, which look more smooth over time. So, but this cannot be seen from these plots. In these plots, they just show you the spatial profile of the activation or supposedly activation. So in these plots, basically, when you see something that is either on the like ribbon-like an exterior side of the brain, or something that is in like a CSF areas, activation that is located in those places, those are like the typical indications that it's something that is most likely either motion or physiological type of effects. In this case, ribbon-like is most often motion. And the reason why they appear as ribbon-like is because if you look at the Ball signal in the brain, the changes in the Ball signal are relatively small, the change that we care about in time, right? When you present a task, perhaps the Ball signal changes 1% or something like that. But if you look at but if the brain actually moves, then the Ball signal in one voxel that might be just perfectly within the brain, now the brain moved and it's a little bit outside of the brain. So outside of the brain, the Ball signal is pretty much close to 0, and inside of the brain is perhaps close to 100. So that if you move slightly, you will see very huge changes in the Ball signal that cover with the gradient of the average Ball signal across all time points in the entire brain. So basically at the borders, you see like, there are very large signal changes that just cover with the actual motion. When a person is moving from back to front, then you see a lot of activation in the front, well, pseudo activation in the front areas and back areas, because that is where the most of the Ball signal is changing. And where the person is moving kind of from left to right, then you see pseudo activations in the left border and the right border, because those are the places where the Ball signal is changing a lot in covariation with motion. And if that motion happens just to be covering with the presentation of the task, because the person just moved a lot, when the task stopped, for example, and when you reach a rest condition, then the person relaxes and makes some motion. And then when the task starts, it just moves again to like an indication that he's paying attention or something like that. Those type of task-related emotion effects, they appear as huge Ball signal changes that appear in this kind of like border-like structure, depending on the nature of the emotion, how the subject effectively moved. In this case, it's probably like a rotation of the head that is somehow either by luck or not covering with the task presentation of the stimulus presentation.
Okay, and might you see this to like a lesser extent around the ventricles sometimes? Like not really a signal in the ventricles, but then you moved a little bit and it's like, oh my gosh, there's a lot of signal, but just to a lesser extent?
But where I didn't catch that portion of the phrase. Could you repeat it, please?
Do you sometimes see this to a lesser extent around the ventricles?
Oh, right, exactly. Yes, in the ventricles as well, because anywhere where if you look at the average Ball signal, when you look at there is a huge, large gradient of that signal, basically large spatial changes in that signal. When the average Ball signal, when you look at the mean functional, for example, we have a plot for that. So let me just show you. Can I take control of your screen for a second?
Sure. Yeah.
Okay, let me see if I have a plot here. Okay, so just something like that. So if you look at the mean functional, it looks something like, let's see, something like this, right? And let me see if I can, just for a second. Okay, let me remove that. Oh, come on.
If you
Um,
click the view overlay checkbox right in the middle.
Right, right, exactly. That's what I wanted to do, exactly. Okay, so basically, if you look at this is the average ball signal across all of the time points in the brain, just one single slice. And black is basically 0 values, and these values are probably close to 100, or perhaps they are close to 1. Why they are close to 1? Oh, because we are looking at the mask, these values now. These are close to 100 basically, and if so, basically in these borders, in these regions, there are huge gradients of the average ball signal. So there are huge changes. If the person just happens to move slightly to the left or to the right, the actual ball signal changes a lot, because a little bit to the left is pretty much 0, and a little bit to the right is pretty much 100. And anything that where you see large changes like that, like here in the ventricles, it happens the same thing. In the ventricles, it's kind of like the opposite, because in the ball signal tends to have higher activity, but it's kind of like the same thing. You see, oops, let's push it a little bit up. Anywhere where you see, because sorry, but the delay is.
Yeah.
So anywhere where you see like changes, that if you move to the left, the image is going to have a totally different intensity in ball signal than if you move a little bit to the right or to the top or to the left. Those are places where if the person moves, you will typically find large changes in the ball signal that correlate with the motion. And then if that motion-related changes actually happen to correlate with the task, then those same things are going to appear to be activation-related. Activation in your analysis. So those are borders of the brain and borders between the brain and the pile or the CSF, the ventricles, anywhere that has CSF area that shows a high contrast because they have different average ball signal values, and to a lesser extent a little bit gray matter and white matter, but those are relatively minor compared to the difference between outside of the brain or inside of the brain, or CSF versus gray matter. So yeah. Boundaries between gray matter and CSF, and boundaries between, with air, those are the two places where you see huge motion-related changes in the ball signal.
So, so based on the kind of weird speech minus baseline plots,
right. So coming back to this guy, right? So yeah. So this subject, contrary to the previous subject, this subject is a little bit worrisome, because even though there seems to be negative association, and we probably don't care that much about negative responses, but it's still showing some indications of motion-related activation, and that is worrisome. So we might try to be a little bit more conservative with motion, or try to how we correct for motion. So how did you specify the design for this subject? Did you remove? You could try, for example, either including higher order derivatives for higher order. Quadratic terms for motion effects. You probably included the default linear, motion, and art, right? Yeah. So perhaps you could try using quadratic terms for motion, just to see whether that helps, or try to include a little bit more conservative art. But given that this already has fewer scans, that might be difficult. So probably I would try increasing the order of the motion covariates in your first level analysis, and that is only going to consume about 6 degrees of freedom for extra, and that might be helpful to remove residual effects of motion-related effects that are clearly motion-related and not perhaps not task-related. So I would probably try that.
Okay. You'd apply that to all the subjects.
Yes, you want to apply that to all the subjects, and the change in the degrees of freedom is going to be relatively small. So for everybody else, it's not going to be much of a noticeable difference. But for this subject, we are hoping that it gives us the edge that we need.
Would it make sense to try it with just this subject first to see if it makes it?
Right, exactly. You could try just for this individual subject and see whether they regenerate the plot and see whether that helps. And then if you find a combination that actually works, then just run that combination for every subject and look at every other subject just to make sure that it didn't affect negatively other subjects. And then if both of these things work, then you're happy to move on.
Okay. All right, I'll try that. And then the one other subject that had a lot of trials missing and a lot of motion was so yeah. This one actually had the lowest number of valid scans and the highest motion.
Yeah, mean motion is ridiculously large for that subject. Yes. Okay, so that is going to be problematic, likely.
Yeah.
So again, look at the time course just to identify whether there was just huge motion in one session or it was just motion all across every session. And in this case, pretty much all across, right?
Yeah.
Okay.
Are you on OpenViews?
No, I don't have field maps.
Wow, and yes, this definitely moved a lot. The 9 millimeter motion is ridiculously high.
Yeah.
So
there's like these big, even after it's like these little jumps.
Yeah, those jumps are residual effects because the motion happened to be like catch like within the time of the scan. Then there are all of these artifacts that cannot be corrected just by a realignment.
Right.
Yeah, and that's why we need to remove. Well, that was huge as well.
Yeah, there's a lot of.
Yeah, so this subject is going to be problematic. But I mean, the good thing is that okay. What do you see in first? I mean, this is all across. So there is, the portions that don't have a lot of motion that haven't been removed still show relatively consistent motion. So that might be problematic. And the question is whether it's correlated with the task or not. So,
I mean, oh well. So I just look at this.
Right. Yeah, that's huge.
When you say that's huge, what are we looking at that makes it seem?
Oh, the total number of scans that are being.
Yeah, I gotcha.
Eliminated trials.
Right.
So
That
there's one
these kept
per-
showing up with my analysis, and I'm like, I don't know what I'm looking at.
Yeah.
It seems very gray.
It's an added regressor for each of the ones that have X.
And the one that you looked at before had like this was grayed out like for a portion of it.
Yeah.
Right. This just happens to be estimable, so it doesn't have enough to be totally non-estimable, the effects that you care about, but that's perfectly fine. That is still going to be, unless you care about session-specific effects, you don't care about that, basically.
Right. Okay. So that's, and then the first level contrast matrix. I think this one looked okay as well. Yeah, there's no black bars.
Okay, that's fine. Could you go back to the design? I'm trying to recall whether SPM has the ability to show you correlation between the different effects. Could you just go to details and look at the design thing? Design orthogonality perhaps allows you to look at
Covariance structure?
No, that is how you estimate the temporal covariance in your data.
Oh.
So that's not, so probably design orthogonality. Could you look at that? Because it might show you, yeah, it shows you the correlation between the different rows of that. So it's difficult to read, but what we care about in that are the 6 rows that correspond to motion parameters. Those are the ones that are right before the ART outlier scans. So those 6 rows corresponds to the 6 motion parameters, and then anything that you care about are the ones that come before that. Those are the ones that the first 4 ones are probably the ones that we care about, and the second one are the first order derivative of the first 4 ones. So what we actually care about is looking at, well, it's too hard to see. I was trying to see whether in these plots we could actually look at the correlation between the motion and the task effects, which would be in this kind of matrix. They would appear in, let me see if I can, I'm still controlling the screen. Yeah, so they will appear in here basically. In here you will see the correlation between these motion parameters and these task effects. But Well, they are not very visible, so perhaps I'll create some plots that allow you to look at those in more detail, basically, just to because that will allow you to see where the motion, because when you have all of these residual motion effects, they have two potential consequences. One of them is just that they force you to remove a lot of data points, and they also increase the amount of ball signal things that are not defined or well fit by your model. So all of those things end up increasing the residual error or decreasing the degrees of freedom, which ends up basically reducing the power. But that is relatively fine. That just gives you more noisy measures. The second thing that can happen with motion is when you have task-related motion, so a motion that correlates with task, and that creates biases in your measures, and that's typically much worse. So you want to, even in these cases where there are a huge amount of motion, if those are not task-related motion, then you might be fine. So I'll try to see if I can generate additional quality assurance, create some additional quality assurance plots that allow you to look at these motion, task-related motion effects in more detail to evaluate where, in these cases, where you have subjects that have huge motion, very few data points, but you still want to know whether you can live with those because they are going to be just noisy data, or whether you should be getting rid of them because in addition to noisy data, they are going to give you biased estimates. So to some extent, you can look at that in the plot, in the speech minus baseline plot. Can you show that plot then?
Oh yeah.
Yeah, the one that you were going to show that I stopped you from doing that. Yeah. Just go back to this for a second. So yeah, to some degree, you can look at where is task-related motion in this plot. If you see anything that is motion-looking effects, then probably you have task-related motion. And if you don't, you probably don't. But it might be good to have additional plots that gives you some idea of or quantify the level of task-related motion effects that you have. So in this case, it doesn't look that bad. Could you click on details and see if you lower the threshold, because it's a little bit more noisy, but that's fine because we expect that to be the case because we have less data points. So just switch it to a single slice just to make it faster, and then perhaps lower the threshold to something like 1 or something like that. Yeah. Well, you see a lot of ventricles, which is never a great sign.
So this is there is activation in the brain.
Something like this. Oh, there we go.
Yeah, right. Something like that. And okay, can you now scroll over the image itself just to look at the different slices? No, sorry, you meant the right thing. Yeah.
That would be motion, right?
Yeah. So all of those ventricle stuff, yeah, and that border. So yeah, there's still a lot of motion-related stuff. So, the same thing as in the previous subject, we still have.
You stop right there.
Yep.
Oh, like this, I find like really well. We go back down a bit. This kind of thing where it just sort of like clipped. It's not really following anything, the anatomy so much.
Right. Yeah, and probably if you show a coronal view, it might be even more visible, that this type of thing, right?
Yeah. And we saw that even in the default set of axials, you could see where it was this band that did not extend to the exterior, nor did it really extend into the cell side.
Mm-hmm.
Right. Well, there is one trick here, which is that just for quality things, we are not displaying anything that is truly totally outside of the plane in this plot, unless you change this to raw, show the actual raw data. We are doing this smoother display, which is trying to like a smooth data, and it's not going to show you that much where something is totally outside of the brain or not. Those are going to be like reduced, unless you choose this option, the raw option, or the overlay contour stuff. What is that contour stuff? Overlay surface on. Overlay contour on. This is whatever. So yeah, you can also use the typical thing, but I use the this, but show the borders, and that will show you whether something is kind of like extending outside of the brain. So that's why. Yeah. So this looks motion, definitely. Yeah, all of that. And I think, let me check this. Yeah. Yep. Probably this.
We are seeing activity in the areas we expect.
Yeah. I mean, there is a mixture of activation, so it's not as large as in the other subject. The other subject was pretty much all motion. This is a mixture of actual activation and motion, I think. So it's probably not as severe as in the previous subject, but it's still.
When you have motion like this, can we also? I guess when I look at this, the way that the activation is lining up with the anatomy, I would want to go back and really check the co-registration. Like, did the normalization work well, and co-registration work well? If a subject that's just moves a lot, Alfonso, seems like that would affect those other operations as well, right?
It could. I mean, to some extent, there are protections against that. So when you run ART is going to create a mask, an average, like a mean functional image that it removes, where it actually removes all of the outlier scans when computing this average mean functional. And that protects the quality of the mean functional is typically a little better than if you just average across all of the time points, and particularly when there is a lot of motion. If there is a lot of motion and you are averaging across all the time points, you typically get a much smoother looking functional image, and when you go to normalize that, perhaps the normalization doesn't work that well. But there are some things to try to correct to avoid that from happening, and one of the things that is trying to help you in that is the ART, which is creating this mean functional that is a little bit more robust. Instead of computing just the average activation across all the time points, is computing the average activation limited only to the valid scans. And that typically works well, just to make sure that the normalization and co-registration and all of these steps are relatively robust against motion. But I don't know, if the quality of the structural, for example, is bad, that might also, well, in this case we are doing MNI normalization, direct normalization, that doesn't affect anything. So that is also, but if you are doing like surface-based analysis, then yes, definitely the quality of your structural also affects a lot with the quality of both the normalization and the co-registration. So if the subject moved during the structural data, then that affects things a lot. In this case, for direct normalization, we are doing the actual direct normalization of the functional data disregarding the structural. So there are fewer things that could go wrong, basically. But yes, definitely go back to those plots and look at the quality of that to make sure that the normalization has worked correctly for every subject. I mean, normalization is going to fail for some subjects, irrespective of whether they moved or not. For, I don't know, some proportion of the subjects, I would say perhaps 5% of the subjects, you're going to get wrong normalization just because it's an iterative process, and sometimes it starts from the wrong initial condition. So it's definitely something to look at.
Yeah, so I mean, here's the functional data with the outline of the MNI.
Yep, that looks fine.
I mean, so this was, I probably pointed out.
It's all the signal dropout at the frontal lobes. That is also fine. That's expected. And then,
I mean, does it matter if there's like little bits that are outside?
Oh no, that's perfectly fine. The boundaries that are displayed are actually 25% boundaries. So that means that in 25% of the subject's gray matter will be outside of that. So that's perfectly fine. Yeah, this case, I don't see anything. Yeah, that's also, well, I don't know what that is, whether that is actually just normal variation, because it looks a little straight, right?
Oh, that's true. Okay.
I don't know if there was any cropping. I don't know, it's subtle, so perhaps it's just.
If we look at the structural data, it's been a long time looking through each and every one of these QA plots.
Right. Yeah, these are the things that I typically just generate like a PDF file, and then I take it with me to have a coffee and go browse over every subject quickly just to make sure that I'm not missing anything obvious in those plots, because there are many plots to look at, and clicking through all of them is a little bit cumbersome. But it's good to at least browse quickly through the plots just to make sure that you're not missing anything obvious, and then go in more detail through this procedure for the subjects that you find that are perhaps problematic because of the histograms, the same thing that we're doing here. But also a very quick browse through every plot is a good thing to do, just to avoid seeing anything, having anything totally wrong that is not indicated by any of the quality assurance plots, the measures that are displayed in these histograms that perhaps are not picking that up.
That's the outline.
The outline, this is the MNI template outline and the normalized structural.
Yeah, that's just to give you a rough idea of where things should be. And in this case, that's perfectly fine. The normal variations that you see around that is totally expected. Is totally within the normal range.
Yeah, I was spending a good amount of time looking through each and every plot pretty carefully. It sounds like that's not necessarily warranted unless you find something that's...
Well, right, exactly. I mean, in my experience, when normalization fails, it fails spectacularly. So you see something that is not even close to being the brain in the right position. I mean, for many other things, we do care about the high detail quality of the normalization. For example, whether you want to, I mean, now that we are getting to surface-based analysis, the pipeline, and I want to make sure that we have the best possible preprocessing procedure for surface-based analysis, I do care about the quality of this normalization, just because it's one of the potential alternatives to generating the surface analysis based on normalized data instead of on the raw data. So for that type of questions, then yes, you definitely want to look at in more detail and kind of figure out where it's failing and figure out why and see how you can make it better. But in general, just for quality assurance purposes, normalization at least wise, when something fails, it typically shows you a brain that is not even close to being an M&A space. So just a very quick glance at the brain should allow you to see whether something went wrong or not.
Yeah. So when you are, one of the ones where I tend to look in more detail is looking at the functional data relative to the structural data.
Oh,
illustration. So to make sure, so what you do is basically you're taking the anatomical outline from the individual structural data and looking at the functional data and trying to, because there you can see rough contours of the gyri and get a sense of how close they are. So you can pick up some errors there, and that would have a big effect on surface-based analysis. But I mean, it's going to affect the volume stuff too. So like we've seen we showed an example from I think it was the S-rate study, S-rate or ACE, where if you look, if you just quickly look, oh, it looks like it's all right, but then you notice that, well, wait a minute, the yellow bumps in the yellow contour are not aligning with the contrast, or the changes in the voxels, the brightness in the functional image. So, well, looks like maybe they're not all that well.
So it's a great fit for a different scene.
Yeah, or there was some sort of
Like
shift.
it looked realistic,
Yeah.
but
Right. Or there was a left-right flip. I mean, there are so many things that can happen. Yes.
Yeah, I mean, when there's something like, so you can see, it's kind of hard to see up there, but there are some of these like deeper sulci areas that when you add the overlay, I guess it is covered actually. Oh, never mind.
wait, you choose a bad example.
I know.
Yeah.
Well, maybe it's not a problem. Okay. So then going back to this subject and their weird like contrast for speech minus baseline contrast, what would you recommend my next step be?
So for this, I'll probably do the same thing as in the previous subject. So try including adding additional, like a second order motion quadratic terms, just to see whether it helps you reduce those motion looking effects in the in here. So the same thing as in the previous subject. Try to change the linear to quadratic in the motion covariates like this for these two subjects and see whether that helps. If it doesn't, then, I mean, this subject, the other one was even more worrisome. This still shows some level of activation that looks like a true activation. So perhaps it's fine. I mean, it's nothing that we couldn't just move on and continue, because those two subjects, at least if those are the worst cases, if the rest of the subjects looks relatively fine, then these subjects could be flagged just by having higher average motion than the rest. So if we need to make sure that our second level analysis are robust to these cases and we are not basically biasing our results for something that is just influenced by these two subjects, we could just include the average motion, for example, covariate in our second level analysis to try to correct for potential effects in our second level analysis that we care about, controlling for the potential effects of the mean motion, which is going to control for these subjects basically, which are showing this much higher mean motion than everybody else. So if nothing works, we could decide to move on. But first, before doing that, let's see whether we can actually find something that works to either remove or at least minimize the amount of activation that we see that is motion looking activation.
Okay, that sounds good. And then maybe just kind of, if I can quickly click through here just to see if all these, I mean, most of these are
right, and then you want to look at exactly, you want to look at these plots for every subject just to make sure that you don't see anything unexpected, because if something hasn't been flagged by the histogram displays, it still might be something wrong that might be worth looking at. So you want to look at the non-variability across the rest of the subjects and whether there is some particular subject that looks particularly strange. This looks a little bit strange, but not terribly so. It's still showing activation in the central sulcus and temporal areas. That looks fine, and the negative activation looks fine as well. This is the subject that didn't show.
Oh, yeah,
We already saw before, right? Yeah. We already saw this guy. This, yeah. Well, intermediate, not terribly worrisome, but a little bit, but it's fine. That looks perfectly fine. Well, yeah, that's fine. Yeah. Yep, that's also fine. Yep.
So every once in a while you get one like 10.
Yeah.
Both ways where.
Yeah, that looks too good. Yeah, that looks too good. This activation, I mean, this portion in here that doesn't look right. I mean, this shouldn't be all that positive, but I don't know. It kind of goes. It's like the opposite effect of something like I think it was this. Let me see. So it's kind of like the opposite in here. In here, you're seeing a little bit of negative activation that shouldn't be there, basically, but it's not terribly worrisome. In this case, you're seeing biases towards the positive numbers. Sorry, number 10. So you are probably seeing a little bit of positively correlated motion related activation, but it's still small because you can still see mostly true activation, so that is probably fine.
That's 12 again, but that's the
right. This was the one that
ventricle activation of the anything.
Yeah.
That subject, the 14, had showed a little bit of that, that blue thing that is covering pretty much all frontal. That looks also, but I don't know. The temporal activation looks fine, so it's probably not. I mean, perhaps these subjects also benefit from having a little bit more robust motion regression, so that's fine. Yep.
Okay.
That looks okay. That looks okay as well. Yep, perfectly fine. Yep, Good enough.
This is-
Okay, so I don't see anything other than the ones that we saw. And I mean, save these plots, and I would say try first adding the quadratic motion related stuff for those two subjects. See whether it helps, and then if it does help, even if only a little, try running the same thing on every subject and see whether you actually got a little bit of reduction of the few subjects that show still residual things that look like motion-related activation, and even though they didn't have that much motion to begin with. See whether that improved the additional introduction of second-order motion effects helped on those subjects as well. But yes, I see like most of us. I mean, it looks pretty good to me. I don't know, Jason, what your thoughts, but I think that this looks reasonable.
Yeah, this looks. The ones that seem the least reasonable were the ones that had a bunch of motion.
Yeah,
exactly.
So
yeah,
that's.
and also the less data to work with, so that also introduces a little bit more noise. So it's
right. And what actually related to that, we go in and Art has sets invalid trials based on motion. Then we also can set invalid trials based on subject's response or something. They made an error.
Right.
Is that included in the valid-invalid trial violent plots that are here?
No, they are not, because those are like treated as any other condition. So perhaps I could add it. There is one way to just add additional. So have Art mark a number of scans that you challenge, like a user-defined list of scans as outliers by default. So perhaps I can make a simpler in this case, because right now the way that I think Sol is modeling the invalid scans is just as an additional condition that we can then look at if we care about it or not, right? So, so in that case, they won't be included in the list of valid and invalid scans by Art. But there is another way to enter invalid scans, which is to let Art forcibly include a predefined list of scans into its own defined list of invalid scans, and when you do it that way, those will be counted towards the invalid number of invalid scans in this plot. So I'll see if I can make it simple so that we can actually use either one of those two approaches.
Is there an advantage to regressing out individual outliers separately versus for, like, right now I'm using for the error trials, just making them all a separate condition?
Mm-hmm.
Is there an advantage doing one versus the other?
Yes, it helps if you remove them in the way that Art is removing. So basically, remove every individual scan, then you are helping. You're removing those scans entirely, even from the residual error of the first level model. If you just remove the average, then there is still going to be some variation that is happening within the scans that ends up being part of the residual error. So in terms of the estimation, as long as your other conditions are not intersecting the invalid scans, so you are already removing those scans from the list of the valid, the speech on baseline conditions, then the only difference is going to be in terms of the residual error. So that is only going to change the t statistics of your first level analysis, but it's not going to be changing anything with the beta values. Basically, the contrast values, the contrast images are going to be the same whether you do it one way or the other. But the SPMT maps for the individual subjects are going to be different, because when you model separately, then you have less residual error, so you will typically have higher t-values, and when you model them individually, you have higher errors, so you will have lower t-values. If you want to, in our FrankLab scripts, actually remove them separately, just mark them as a non-parametric. Remember the NP mod field, just mark that condition that you want to estimate non-parametrically, and that will actually estimate that condition separately for every trial, the invalid ones, so that will be effectively equivalent to the way that Art does it.
I see. Okay. Okay. I think those are all the major ones. I'll look through these again, and based on the knowledge that I've gained in this brief session, if there's anything else,
I'm anxious to see what happens when we add those other motion, higher order motion.
Oh yeah, yeah.
variance because of that.
Right, and I'm trying to also incorporate the ComCore strategy into our potential ways of kind of trying to remove these type of things and how to reduce the potential residual effects of motion and physiological effects in our first analysis as well. So I'm hoping to have that available soon. I was originally doing for this experiment, which has a lot of motion, but in this case, it's probably not that needed because there's only a couple of subjects that show a lot of motion. So, but in any way, I'll let you know when that is available, so you can also give that a try. It's an alternative way of removing potential residual motion or physiological effects that are in the data that even after all of the things that we are controlling for.
Okay.
All right. So, you have Megan. You have some questions?
Yeah, I think it might be easier for you to do it, Alfonso, on your computer and share, just because I can tell you the directories will be bigger.
Sorry, I didn't quite hear. Could you repeat it, or could you get closer to the mic?
Oh, sorry. I think it might be easier if you do it on your computer and share it, because I'm looking at everything through a VNC session. So I think if we shared my computer through the VNC section, it would be, and then shared that with you through Zoom, it would be both really slow and very small.
So do you want me to log in to one VNC session? And let me see if I have one open.
Oh, that would work. I was just going to say you could go to the directories. I'm pretty sure you have access.
Well, I think you still have to use VNC.
Oh, okay. But, yeah, so whatever's easiest for you.
And I have to leave in about 20.
I don't think you're going to gain a lot from the questions I'm going to ask.
Well,
because some of them are literally, I've gone in the directory where I thought they were made and they're not, or like I can't open them. Like I did the pre-processing manually before the new pipeline, and so I got a pretty good guess that it's pretty good for all the overlays and all that good stuff. And so now I'm basically just trying to open and look at it again with the created pipeline and don't know where everything is,
Sure.
which is a silly question to ask, but one that. And also, I only finished writing these this morning, so I haven't looked extensively, but I have you here. I figured I'd ask. Save myself some time trying to find plots I can't find.
I'm trying to generate, I didn't have a VNC session open, so I'm trying to run one, and for some reason I'm still waiting for the MyQ VGL thing to start. So I don't know if you want to still try to share your screen to see if that is more efficient, because my screen is going to take, it seems that it's one of these days that
it's going to be tiny.
Or if you don't think that we actually need to see it, then you can just, we can perhaps go without actually seeing it.
That's possible. Did you know the directories where everything lives?
so if you want to do it away for Alfonso's,
We can do it through mine if you still get the Zoom.
yeah, you should.
I should have it. Okay, just send it to
I think it's probably best because my session key VGL is still waiting, and it looks like it's going to be there for a long time. So.
All right, hold on. Let me do that. Yeah, yesterday it was much better today. Yesterday the cluster was really dragging its feet.
Yeah.
Sorry, I was logged in. Maybe you could. Sure, you sent me the link. I'm not getting it.
Sent to mmct@bu.edu.
Yeah,
Just two things mildly urgent. Just the name.
mildly urgent. So.
I didn't want to cause alarm.
Sounds like a salsa name. Like this is mildly urgent. Is it really urgent? Yeah, the link's not showing up, but I can just sort of walk you through the directories in the meantime. So I ran pre-processing and first level analyses for, I only have so many subjects, like 6 or 5. And it does, so it creates an offshoot from your main FL directory that's derivatives, right? That's basically where all the things that came from your config files end up.
Mm-hmm.
And then
Hey, came back. Okay, so I have a VNC session. Do you want me to share mine then?
Sure.
thank you.
Okay, no problem. Sorry that it took so long. It's, I don't know. Let me, okay, let me see if I can share my window then.
So yeah, so derivatives is everything created by the pipeline, and then MNI space is because I ran the MNI space pipeline, and then it runs by subject, and then it goes results, right?
Right, so when you import data, it goes into the sub something folders. When you run preprocessing pipelines, it runs into the derivatives folder with a name, with a subfolder's name for each pipeline. And then when you run first level analysis, they go into the first level results and the name of the first level analysis.
Oh, okay. So, so only the first level analysis goes into the derivatives MNI space subject number. Pre-processing would go into where?
Right, let me show you. So repository, so this is the repository. Your experiment was, let me see, your experiment was the RAI experiment, sorry?
ECOG, sorry.
So the ECOG experiment. Yeah, right. Okay. So in here you have a subject that contains the data, the raw. When you import it, it goes into these folders. These are the actual raw data that you import for every subject. Then you run first level analysis. Sorry, then you run preprocessing stuff, and it goes into derivatives. And inside derivatives, you're going to have a different subfolder for every different pipeline that you run. Right. So if you run just one pipeline that running your functional structural data through the MNI converting pipeline, then you just have a folder here, MNI space, and within that subfolder you have every subject again. And these are folders where every subject, where you will find the data for every subject that contains that data preprocessed through that particular pipeline. And then if you use that particular data for that particular pipeline to run any type of first level analysis, then you will have those in here. And here you will have the actual first level analysis. So this is telling you that this is actually this data from this subject that actually after it has been run through this pipeline and you have estimated this first level analysis. This was kind of like the different portions of the folder where the first level analysis results go.
Okay, so if I wanted to check how well that did, the QA plots to those.
Okay, and if you have, let me just, let me see, let me add. Let me just check the plots for that. If you want to look at the QA plots for all of them, just enter the name of the experiment, and that should be it. Now you have to enter the name of the pipeline as well. Sorry.
Oh, okay.
Yeah.
Okay.
And in there you have all of the, well, but you only created for a couple of subjects apparently. Is it true?
Oh, yeah.
I
made the QA plots for a few subjects.
Okay, so here you have the quotation plots for those.
Oh, okay. So I guess, all right. So you don't, yeah, this is what I mean. Like
Let me see, and you have all of the, yeah, you can create it.
Did I only run like certain types? Because I was looking at the drop-down menu and I didn't try all of them. But...
Looks like you have. Looks like you have all of them.
Okay, not all of them. Sure.
Oh, like
right.
But maybe I was just looking at one of the subjects that had one hand. All right. Well, those look, I mean, not promising, but it was
way up here. You're there.
good there.
Right.
It's one subject, so like.
Okay. Yeah.
But yeah, I also was using what was already segmented as baseline by like earlier analyses.
Oh
So
yeah.
I need to make sure that actually is baseline. I read the script, but I didn't, baseline. I'm kind of like, okay, well, I'm not really sure what use is baseline.
I remember in one of them there was an implicit baseline. There was one where they just took the time between trials, and then for later subjects there was actually a specified baseline trial.
Because they all had like a specified, like, when you looked at, they gave you times for baseline.
Oh, okay.
And all the other times I figured out where they got it from. The baseline, I'm not really sure.
Okay.
So this is more of a problem higher up in the pipeline then. Like in my inputting for the config files, I had to put in all the onset times. Which were more or less, like, they weren't random, but they were very specific, like with 7-digit decimal times. So
Yeah. The other thing. Oh, Alfonso. Still there?
Yeah, go ahead.
Yeah. So with continuous acquisition experiments, like all the repetition suppression experiments, basically.
Right.
At one point, I mean, you had mentioned that we should, if we're doing the slice timing correction, then you should adjust all of the onsets of the individual trials.
Oh, right. Yes, and let me actually double check, because SPM, I know SPM 12, some of the new releases have actually changed something about that. So I need to double check. So yes, typically the way that at least our processing pipeline does it is that when you do a slice timing correction, every slice gets corrected to the mid slice, and the mid slice is the actual mid time slice. So whatever happened at the middle of the TR, wherever a slice was acquired at that time point, that is the reference slice that is used by a slice timing correction to correct everything else. And that means that basically all of that you are getting a scan for a time point that corresponds to the mid of your acquisition. So whether you want to correct for that or not is up to you, because typically the half the time of a TR is not a huge difference in time. But if you want to actually try to correct for all of the onsets and to be able to correct for the fact that you are not specifying 0 as the time at the beginning of the first acquisition, but 0 is actually the time of the middle of your first acquisition, then you can change the actual onset times to reflect that. But I seem to recall that SPM 12 changed something about that, about the way that it specified the micro time resolution, things that were related to this, basically. When basically the question is, when you specify a number of onsets and times, SPM has a way to derive the actual regressors by convolving that with HRF, but it's not actually convolved at the actual resolution of your scans. It's actually converted to this micro time resolution first, and then converted back. And when at the process of doing that, I think it's doing some correction for this. So I'll have to go and look and check, because I'll double check and make sure that whether you still need, in previous versions, you need it when you apply the slice timing correction, you need it to correct for that. If you're using the mid slice as the reference slice, you need to correct, and if you were using the first slice, you didn't.
I also think I need to look deeper into whether these onset times match up.
Right, but it might be that in the new versions it's not need to correct for that.
From the scanner, right?
I thought I think the onset times for that study, and I could be wrong, is based on the MATLAB script.
Yeah, which I've been running.
Okay,
That's where I got them.
No, but I mean like the actual, like the experimental MATLAB script that gets run, and so.
So how do I sync them with the scanner?
I think there's in all of if Jen set up the experiment, there's usually a line of code that was like wait for a specific, like the first scan, and then that gives you a reference time to calculate the rest.
That would be the trigger, right?
That would be the trigger.
Okay,
Yeah.
because it is checking for the trigger.
Right, but there should be like one at the very beginning that checks for the first trigger, and then in like MATLAB time, whatever time, arbitrary time, it's like a 5-digit
That's set as
number.
0.
That's set as 0, so you need to like
So it's everything off of that time.
Yeah.
Which the trigger is that start of the acquisition is the trigger, or is that once the acquisition starts to do?
No, the trigger's the
Well, the trigger time, if you have to look at the code. Jen probably has MATLAB structure, like data that saves this already, but trigger would come in, that would mark the time of the acquisition. When that comes in is the time of the onset of the scan.
Okay,
But-
so that's.
But
what I-
there's going to be a wait for, right? So I guess it should still. My guess is that that would be time 0 of the start of the first scan.
Yeah, that's I believe what it's doing.
Okay.
And I got all of those from her script, which I did go through her code. It does check for the trigger, and then once there's a trigger, then it checks for everything else is based on the auditory from the MATLAB experiment. But it doesn't start until there's a trigger, I think.
Best way to check for that is to run a bunch of the subjects with what you think is best, and just look at the speech meta
That's what I
baseline.
was trying to do, because there's like all these different conditions, and I just did speech and baseline for now.
Just look at speech
But first
baseline.
one is not promising. But I will look at the later one.
I have to run. Saul, can you save the recording and
do whatever.
Alfonso, thanks a lot.
No problem. I was actually looking at all of this at the macro. Sorry.
Sorry, we didn't catch that.
Sorry, I was looking at the micro time onset thing, and it's right. The micro time onset in the new version of SPM is actually defined as the mid slot. So that's perfectly fine. When you do apply slice timing correction, everything will be. You don't need to actually manually change the onset time.
Good. So right now we're working under the assumption that all my onset times are right, and so I'll just keep running them on all of them and see if they look speechy, and if they all look as bad as that one, then I will come back.
Sounds perfect. Yep.
All right, thank you.
No problem.
The one reason I brought it up is because if you were using onset times, that if Jen like ran it a couple different ways, and she may have ones where she just shifted all of the onsets by a certain amount.
This is confusing to me because I thought that. You mean ran the scripts a couple different ways?
Yes.
Okay, because I was gonna say I thought this experiment was different.
Yeah, but in terms of SPM, when you specify the onsets, the durations of these kind of config files, the 0 corresponds to the beginning of the first scan. So that's the reference time for what SPM is about when they find the first analysis.
Okay. Cool.
Even if you apply slice timing correction and your reference slice is actually in the mid of the first scan, that doesn't matter. Actually, SPM does correct it, at least now for that.
Okay, good to
Okay.
know. I've been very fearful of making the wrong times. So. Okay.
Okay. I
Thank
think
you.
that's it.
Okay, fantastic. And,
Oh, Alfonso, actually, I wanted to know. I mean, do you have time to meet briefly now? I just had
sure. Okay.
a question. I'll. Yeah. You can.
I was gonna say I won't cut in.
Yeah. Let me stop recording.
Going off book.